Hi there. In this video, we will use the finite elements derived in the previous video to work a real problem. And what we're going to do is we would like to model a bar that is undergoing axial vibrations. It has a length L, capital L, and it's fixed on the left-hand side. That is to say, the displacement on the left end is 0. In general, we would like to try to model this using finite elements. In the first case, the blue case here, we look at one element. The length of that element is obviously L, since there's just one of them. And that element has two nodes, one on each end of the bar. If we move from 1 to 2 elements in the red, then we end up with a third node in the middle. And the length of each element is just L over 2, which makes sense. Moving on to 3 elements, we see we get an additional node, 2 middle nodes in this case, and the length of the element is L over 3. And in general, we can say for n elements, there will be n elements of length L over n, and there would be n plus 1 degrees of freedom. So for n elements, just write that, n plus 1 degrees of freedom. And again, just to remind you, the idea here is we're taking a continuous system and we want to replace it by a discrete system. So in other words, instead of knowing the displacement at all points along the axial direction, we choose to only find it at a finite number of points. And by doing that, we can take complicated problems, even though this is a fairly simple one, we can take more complicated problems and have a computer find us solutions to that problem. So that is the goal here. So let's look at the element matrices that we derived previously. And let's start off with the case of one element. So what we'd like to do is we would like to model this bar undergoing axial vibration using a single element, and specifically what we would like to find is the fundamental frequency. And just as a reminder, if you've got a single degree of freedom system, you will only have one natural frequency. 2 degrees of freedom, you have 2 natural frequencies. In fact, you have a natural frequency for every degree of freedom. And the frequency that we're after is the lowest of these frequencies, which is the fundamental frequency. The lowest, the smallest in magnitude is what I mean by the lowest. All right, so if we look at one element, I will use lowercase m to denote the element mass matrix and uppercase m and k to denote the global matrices. It's rho times A times L divided by 6 times 2, 1, 1, 2. Let me point out that this L here is a lowercase l because it's the length of the element. And now we need to write the length of the element in terms of big L, which is the length of the beam, the length of the bar, excuse me. So little l, the element length in the blue case here, is just equal to capital L. So I can just rewrite this as rho times A times capital L divided by 6 times 2, 1, 1, 2. And what I'll choose to do is just group these constants as a single constant, reminding you that rho, A, and L are a combination of material and geometric properties. And I'll just rewrite this. I'll call it Cm. And I choose to write it this way. It will become obvious in a little bit why. Okay. And similarly for the K matrix, which is equal to E times A divided by little l, times 1 minus 1 minus 1 and 1. And again, little l is equal to big L for the case of one element, so this would be E A over capital L times 1 minus 1 minus 1 and 1. And I will call that CK. Okay. If I were to move to 2 elements, let's see if I can squeeze this in here. Then what would happen is the M matrix would equal Cm. Well, let's write it in longhand. So if I substitute L over 2 now for little l, I will end up with rho A L over 6 times 2. Times 2, 1, 1, 2 equals Cm and I'll write it like this: 1 divided by 6 times 2 into 2, 1, 1, and 2. And similarly, I will find the K matrix, which is equal to EA divided by capital L times 2, where I've substituted capital L over 2 here for little l. And that is equal to, or that multiplies 1 minus 1 minus 1, 1. And I will rewrite that as CK times 2 times 1 minus 1 minus 1, 1. And what I'm hoping you're going to see here is a pattern developing, is that we divide, this number here is the number of elements, and this number here is the number of elements. And depending on how many elements we use, we just put that in there to get the equivalent mass and stiffness matrices. I also want to point out, it should be kind of intuitive, that as the element gets shorter, the magnitude of the mass matrix will get smaller because there's less mass. That's why we are dividing by n here. Whereas as the element gets shorter, the stiffness gets higher, it gets more stiff. That's why we multiply by the number of elements here. All right, so let me just write that out in general terms. So if we have n elements, we find out that the mass matrix M is equal to Cm times 1 over 6 times n times 2, 1, 1, 2. And we find that little k is equal to Ck times n times 1 minus 1 minus 1 and 1. Okay. So now what we'd like to do is use a single element to solve for the fundamental frequency. So let's see how we go about doing that. Well, in the case of the single element, the global mass matrix M is just the same as the element mass matrix. So it is Cm times 1 over 6 times n times 2, 1, 1, 2. And same thing for the global stiffness matrix. It's equal to Ck times n. N in this case is 1. So that's 1, and that's 1. And then 1 minus 1 minus 1 and 1. Okay. Now here's the interesting thing. In order to apply the boundary conditions, we know that node number 1 is fixed. In other words, everything that corresponds to node 1, meaning your first row and first columns of your matrix, can be eliminated because they contribute nothing, because they're always going to be multiplying 0. So we reduce the order or the size of the matrix to actually make it more computationally efficient at the same time. And what we'll do here is I'll just cross it out. So I'll cross out the first column and the first row from each of the mass and stiffness matrices, and I'm left with a 1 by 1 matrix, which is really just a scalar. All right. So how do we now solve for the fundamental frequency, or the natural frequencies in general? So we want to solve for omega, and we take the determinant of k, and this is the global k, minus omega squared m, and that's equal to 0. So in this case, there's only one element. It makes it really easy to take the determinant. The determinant is just itself. So the determinant of the mass matrix is Cm times 2. Cm times 2. Oh, divided by 6, excuse me. And that is, well, let's write it this way first. Let's skip a step. So minus omega squared. Oh, I've totally messed this up. Let me just rewrite it, sorry. K is Ck times 1 minus omega squared m, which is omega squared times 2 over 6. Okay. Which is a third, obviously. This is Cm equals 0. So solving for omega, we get omega squared first. We get omega squared is equal to ck over cm times 3. Excuse me. Times 3, yeah. And I'm just going to call ck over cm, I'm just going to give it a name and call it a, or a squared is even easier. And you'll see why I did that in a minute. So this is a is equal to the square root of ck over cm. Right? I'm just going to write this as 3a squared. This implies omega is equal to root 3a. Okay, and root 3a, by the way, let's just write it numerically, is 1.732 times a. So what's interesting here is we could almost have just ignored the cm and ck initially, and all we do is multiply our frequency by a. And you're going to see that's something we do in the next video going forward, is instead of coming up with any material and geometric properties, just assume at the beginning that all of that comes to 1, so that a is just 1. And then what we find is at the end, once you calculate your frequency, you will just scale it by a. So if a is equal to 2, you just multiply your frequency by 2, and it's pretty simple. Okay, so again, in going forward, we will ignore the cm and ck when solving the determinant equation. And then we'll account for that just by multiplying the frequency by a at the end. So let's go and have a look at what happens if we model this with two elements. All right, so for 2 elements, so we now find that m is equal to cm, we did this before on the first page, over 12 into 2, 1, 1, 2. Okay, which is equal to a over 12. Well, we'll leave it in that form for now. All right, and then the K matrix, we have this 2 is just CK times 2 times 1 minus 1 minus 1 and 1. Okay. So again, I'm going to ignore the CM over, the CM part, and I'm going to ignore the CK part for reasons we discussed previously. So in finding the global matrix, what we're going to do is this. Let me draw a little diagram, maybe that will help. So we've got one element like this. We've got a second element, let's say, like this. We've got a common node in the middle. I haven't drawn it to scale, but assume that each element is the same size, L over 2 and L over 2. What happens is we need to construct the mass matrix. The mass matrix is now a 3 by 3 matrix because they're 3 degrees of freedom. And we have to insert the element 2 by 2 matrix and place it within this 3 by 3 matrix. And the way it works is this. The first thing I do is I create a 3 by 3 matrix that I fill with zeros. So I create, as it were, a blank mass matrix of the correct size. And just remember where this comes from. This comes from the fact that we have an equation of motion that looks like m x double dot plus k x equals f, or 0 maybe in this case. Okay. So the mass matrix has always got to have the same number of degrees of freedom as the system. That kind of stands to reason. Okay. So if I take the blue matrix, I notice that these nodes here, if I number them, are nodes 1, 2, 3. And these are columns 1, 2, and 3, and rows 1, 2, and 3. Okay, now we're almost there. Give me one more minute. So the blue mass matrix corresponds to these coordinates here. The red corresponds to these here. And you can see what's interesting is this node right in the middle has a contribution from both elements. Well, that makes sense because that node affects both elements. And similarly, the nodes on the end only affect one element, and that's what you're seeing. So the idea is to take the element mass matrix and to find the global matrix by assembling them. And in effect, what you're doing is superimposing them, which is a fancy way of saying adding. So let's see how we do this. The mass matrix based on this would be equal to, I can do it in black, I suppose. It's equal to, I'm just going to carry the Cm for now, even though I'll leave it behind later. Cm over 12 times, and let's see how I want to do this. So here are the contributions from the blue. It's 2, 1, 1, 2. And the contribution from the red is 2, 1, 1, 2. And of course the rest are zeros. Oops, let me just write that in line. So in fact what this looks like is Cm over 12 times 2, 1, 0, 1, 4, 0, 0, 1, 2. And that is the global mass matrix. Similarly, we'll come up with the global stiffness matrix, which would be Ck times 2 times, and I'm going to write it in assembled form all at once. It's 1 minus 1 minus 1, 1, plus 1, minus 1, minus 1, 1. These are zeros. And again, we can rewrite this as Ck times 2 times 1 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 1. All right, and exactly the same way as before, we can eliminate the first column and the first row of each of these. Whoops. And then we want to solve for omega by taking the determinant of k, global k, minus omega squared m. And we mentioned last time how I can ignore the Cm and the Ck. I'll just cancel that for now. And we're just going to multiply the result by a, where a is the square root of Ck over Cm. Right, so what does this look like? And that's equal to 0, which implies that the determinant of 2 times, let's write this out, 2 minus 1, this is this matrix here, by the way, what's left of it, 2 minus 1 minus 1 and 1. Oops. Minus omega squared over 12. I made a mistake here. I realize that's not a 0, that's a 1. Sorry about that. 4, 1, 1, 2. And that's got to be equal to 0. All right, and in the interest of saving time, I'm actually just going to give you the answers. We find that the fundamental frequency, or the natural frequencies, I should say, are equal to 1.611a and 5.629a. Obviously, since a is positive, this 1.611a is the fundamental frequency. And by the way, let me remind you that that compares with the 1 degree of the one element. The single element, we got 1.732 here, 1.732. So this is slightly lower. Now, interestingly, if we look at the exact solution, we know it's a very well-known classical problem. The exact solution to this is actually omega, the fundamental frequency, is equal to pi by 2. Okay, and you know that pi by 2 is like 1.57 something, 571 I think it is, times a, obviously. All right. I'll leave that as an exercise for you guys. It's just linear algebra. You should be able to solve it. The other thing you can do is carry through your constants Cm and Ck. Do not eliminate them at the beginning, and convince yourself again that you could just multiply the frequency by A. You'll see it come out. Now, for a 3-element model, it's just computationally, it's not impossible, but very, very tedious to do it by hand. Probably be next to impossible at anything bigger than that. So what we'd like to try to do is generalize this a little so that we can implement it in a computer code. And by the way, computer codes now can solve the determinant problem for the eigenvalues and eigenvectors in a single line of code, as opposed to 4 or 5 pages of written calculations. All right, so if I look now at n elements, and we mentioned this before, that in order to construct the mass matrix, which by the way has n plus 1 degrees of freedom, the mass matrix is equal to, let's see how I want to do this, let me just use some colors. We have a matrix here, let's say, 1 element. We have a second element here. Let's say we have a third element here. All the way down. Do that in black. And the idea is dot, 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 dot. This continues. Let me make this bigger. And then eventually you have like an element down here at the end. All right, and this is all part of one matrix. These, of course, are the element matrices. And in the case of a bar, there are 2 by 2 matrices all of it. This one here, and this one here, and this one here, and this one here. Okay. Then what we do is we know that the mass matrix is equal to Cm times 1 divided by 6 times n. 2, 1, 1, 2. We know that the K matrix is equal to Ck times n times 1 minus 1 minus 1 and 1. And we've also discussed that what we then do, I'll do it here so it's all on the same page, is we take the determinant of K minus omega squared m, and a reminder that you first got to eliminate those degrees of freedom that are fixed. Right? Therefore, we can get the eigenvalues from this. And we know that frequency, or omega, is just the square root of the eigenvalues. Since actually with the eigenvalues, we're solving for omega squared. And by the way, it's that times A, having ignored the Cm and Ck. Okay. So finally, I'm just going to write the steps, and this is in preparation for the following video where I will take this and implement it in code. And we will follow directly off this last page. So let me just summarize it, what we're going to do next, and then we'll end this video and continue in the next one. So, for each element, one, find the element matrix, or matrices. Find element matrices, call it, for n elements. We've shown how it's a function of n. Okay. The second step is to expand each element matrix to global size and correctly place it. So what do I mean by this? We create a matrix that's full of zeros, that's the size of the global matrix, and then we place the element matrix, which is a 2 by 2 matrix, somewhere within that n by n matrix. So expand element matrix to global size and correctly place it. Might not be the best description in English of it, but I think you know what I mean, having gone through it. You create a big matrix and you place the element matrix within it. Size and correctly place it. Okay. Third, what we do is we add, superimpose is a fancier word, we add these expanded matrices together to form the global matrix. Let me write that. Add these matrices together to form global matrix. And this is the process of assembling it, as they call it. All right. The fourth step is to remove those columns and those rows from your global mass and stiffness matrices that correspond to your fixed degrees of freedom. So remove columns and rows corresponding to the fixed degrees of freedom. Okay, 5. We've got to do this for both. Do this for both mass and stiffness. Then we solve the eigenvalue problem. So solve for eigenvalues. And the eigenvectors, I guess, although we're only using the eigenvalues for this problem. And then finally, we solve for the frequencies by taking the square root of the eigenvalues. And then, of course, we find our fundamental frequency by looking at our frequencies and picking the lowest of them. All right, so that's where I'd like to end this video at this point. Hopefully you found something useful in here. If it's a little bit complicated for you, stick around to the next video, and I think a practical example will explain a lot. If you found this to be useful, please go ahead and give it a thumbs up. That will help other people get to see it too. Thank you for watching, and we'll catch up with you in the next video. Bye-bye.